In this video, we solved problem 15.8.010 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to use Stokess Theorem to evaluate the line integral over C of f dotted with dr, where C is oriented counterclockwise as viewed from above. And we are given this field and a surface given by the equation z equals 36 minus x squared minus y squared. And we're just talking about the part of the surface where z is greater than or equal to 0. Now, because z is raised to the first power and x and y are both squared and they have the same sign on those coefficients, we know we are looking at an elliptic paraboloid. Because the coefficients of x squared and y squared are both negative, we know that elliptic paraboloid, is flipped upside down. If this was z equals x squared plus y squared, we'd have an elliptic paraboloid facing up. Since we've multiplied that function by -1, that flips it upside down. Adding 36 moves the whole thing up 36 units. And so we're going to get something like this. Now we want the part of the elliptic paraboloid that is above the xy plane because we want z to be greater than or equal to 0. So this is the part that we're considering. So that's our surface S. Now C is the boundary of S whenever you're referring to Stokes' theorem. And we want C to be oriented counterclockwise as viewed from above. So if we're looking down a unit normal vector, which is going to look something like this. Or maybe we should look at the unit normal vector at the very top. That orientation of C will be counterclockwise relative to our perspective if we were looking at it from the top here. So C is going to go around like this. It's the bottom. That's the boundary. And Stokes' theorem says that under certain conditions, the following is true. The line integral over C of f dotted with dr turns out to be the same as the surface integral of the curl of our field dotted with the unit normal vector times a little surface area piece. Now, we have been asked in this problem to evaluate the line integral over C using this theorem. So they're saying, find the value of this using the value of this. So in practice, what we're actually going to do is evaluate this surface integral rather than evaluating this line integral. If we wanted to, we could verify the theorem by evaluating this line integral and evaluating the surface integral and seeing that we get the same thing. Now, this is not always true. We should check and be sure that those conditions are met. Let's look at the conditions. And here I have listed the conditions for us. The first is that S is an oriented surface with a unit normal n hat. So we've got an oriented surface. It has a top side and a bottom side. And we've got an n hat, and we'll choose a positive orientation. Well, not a positive orientation. We'll choose to orient that surface upward so that n hat is pointing upward. It has a positive z component. And we want that oriented surface with a unit normal n to be bounded by a piecewise smooth, simple closed curve C with positive orientation. And this is smooth, so clearly it's piecewise smooth. It's a simple closed curve. Positive orientation just means that it's oriented in a counterclockwise direction relative to the normal vector, as we were discussing earlier. So it's counterclockwise as viewed from above, and that's true for this orientation of C and as given in the problem statement. So if I've got my oriented surface with unit normal n with that piecewise smooth, simple closed curve boundary with a positive orientation, if both of those hold and the component functions of our field have continuous first partial derivatives on an open region containing our surface and containing its boundary, then this line integral is equal to this surface integral. And if we look at this, remember, this is just the field written in terms of your component functions m, n, and p. I prefer component form. I prefer to write it this way. The x component is 7x times z. The y component is y. And the z component is 7 times x times y. So yes, those are polynomials in x, y, and z. They clearly have continuous first partial derivatives for all of three-dimensional space. And so all three of these are satisfied. And that means that I can evaluate this line integral and I can evaluate this surface integral, and they will give me the same result either way. Okay, so again, the problem statement says, use Stokes' theorem to evaluate this line integral. So we're saying to find the value of the line integral, let's evaluate the surface integral. So that's the plan. Actually, I don't think the line integral would be that difficult. Well, I mean, maybe. We're going to have a parameterization of C involving sine and cosine. So yeah, that might be a little bit involved, writing that field in terms of T and then taking that dot product, but it might not be that bad. But the problem statement says evaluate this using Stokes' theorem. So we will evaluate this. And if it doesn't take too long, I might evaluate this one as well, just to see that we get the same result. Okay, so remember, every time you're evaluating a surface integral, in practice, we need to write everything in terms of two variables. So what we would typically do, rather than evaluating the integral over the surface, or in order to evaluate the integral over the surface, is we would look at the projection of that surface onto the XY plane. Excuse me. So the projection of this surface onto the XY plane is this disk in the XY plane. And we know that the equation of our surface was z equals 36 minus x squared minus y squared. So when z is equal to 0, we get that curve, that piecewise smooth, a simple closed curve, boundary C. So in z equals 0 here, if I rearrange that equation, I get x squared plus y squared equals 36. So the region that we're interested in, is a disk of radius 6, centered at the origin. We typically call that projection of the surface onto the XY plane, the region R. So we're going to evaluate the double integral over R of the curl of f dotted with n hat. Now, if our surface S is given by z equals little g of x and y, and we want the unit normal vector to point upward rather than downward, we would define capital G of x, y, and z to be z minus this function, little g of x and y, where little g of x and y is this 36 minus x squared minus y squared. So now we're thinking of this surface not as a function of two variables, but as a level surface of a function of three variables. In that case, in order to evaluate the surface integral, we will take the curl of f and we'll write it in terms of x and y only. So we'll leave the x's alone, we'll leave the y's alone, and then we'll replace z with whatever z is in terms of x and y. I could have easily written g of x and y, but I'm just emphasizing that this is z as a function of x and y here. So I'm going to replace all of my z's with 36 minus x squared minus y squared. And then I want to dot that with n hat times ds. Now the unit normal vector can be found by taking the gradient of capital G, that's going to give us a normal vector, and then dividing by its magnitude. But then the surface area is actually the magnitude of capital G, or the magnitude of the gradient of capital G times dA. So remember, we've done this before. This is the same as this. That's my unit normal times ds, which was, remember, that square root of 1 plus the partial derivative of z with respect to x squared plus the partial derivative of z with respect to y squared. That is the gradient of capital G times dA, where dA is dx times dy, or vice versa. Those will reduce every time, and you're going to get this. So this n hat ds is replaced by the gradient of capital G, which is not a unit normal vector, it's just a normal vector to the surface, times dA, where that's an area piece, and that would be dx dy if we were in rectangular coordinates. We're probably going to switch to polar, but you get the idea. Okay, so that's the plan. And because we are using the upward unit normal, we want G to be Z minus little g of X and Y. Now I love this formula because it tells you exactly what to do. The first thing that we'll do is we'll find the curl of F in terms of X and Y only. It's very easy. Now, first we need to find the curl of F, which we can think of as a cross product with the del operator. So you've got those operator components of the del operator in the second row of that determinant form of that cross product. And the components of F are down here. Now F had these components for our problem. 7xz was our X component. Y was our Y component, and 7xy was our Z component. Now we want to compute the curl. So we're going to cross out the row and column containing I hat, and then we're going to multiply I hat by the partial derivative, with respect to Y of 7 times X times Y. And then we're going to subtract the partial derivative with respect to Z of Y. We multiply that by I hat and then add -1 times, cross out the row and column containing J hat, the partial derivative with respect to X of 7xy minus the partial derivative with respect to Z of 7xz. Multiply that by J hat, and then we add this function times K hat, or cross out the row and column containing K hat, the partial derivative with respect to X of Y minus the partial derivative with respect to Y of 7 times X times Z. Okay, there are no X's here, so that's 0. There are no Y's here. This is constant with respect to Y, so we get 0 there. There is a Y here. I'm thinking of this as the derivative of a constant times Y. The derivative of a constant times Y is just that constant. There are no Z's here, so it's constant with respect to Z, so we'll get 0. Here I've got a constant times X. The derivative of a constant times X is just my constant. And here I have a constant times Z. The derivative of a constant times Z is just the constant. So after simplification, we get a curl of 7x times I hat plus -1 times 7y minus 7x times j hat plus 0 times k hat. Now I would distribute that negative and then write that in the reverse order because I want my positive term to come first, but that's not necessary. Now I would write this entirely in terms of X and Y only by replacing any Z's with 36 minus X squared minus Y squared, but it turns out that this time the curl does not depend on Z at all. So there's nothing to replace. I will write that down. In general, you would substitute the equation for Z in terms of X and Y. Into the form of the curl of F, but that's not necessary this time. Okay, so we've got the curl in terms of X and Y only. Now we need the gradient of capital G. So first we need to find capital G, and then we need to compute its gradient. And again, we're saying Z minus that function in terms of X and Y because we want that unit normal vector to point upward rather than downward. And we're thinking of our surface as a level surface of this function of 3 variables. So we have Z minus the quantity 36 minus X squared minus Y squared. You can distribute that negative if you want to. And then we'll compute the gradient of capital G, which is easy enough to compute. The derivative of this with respect to x is 2x. The derivative with respect to y is 2y. The derivative with respect to z is 1. Okay, so now I've got this as my gradient, and that is my curl in terms of x and y only. And now the formula tells us exactly what to do. We're going to compute the dot product of those. That will be our integrand. This is really, really easy. It's very straightforward. Not difficult at all. So we're taking an x component and multiplying it by an x component, and then adding the y component times the y component, and then adding the z component times the z component. Remember, dot product should always give you a scalar and not a vector. So multiply and add, multiply and add, multiply. All right, of course, 0 times 1 is 0. And if we distribute here, we get 14x squared. If we distribute here, we get 14xy. Distribute over here at the end, we get negative 14y squared. If you want to, you could factor out that 14. I probably will. Well, I will, actually. So I've got 14 times x squared plus xy minus y squared there. Okay, so that is our integrand. So the line integral over c of f dotted with dr turns out to be that surface integral, which is equivalent to this double integral over r of our integrand, the curl of f dotted with the gradient of capital G. Now, since our region is a circle, it's a disk, a circular disk. I guess all disks are circular, aren't they? I guess in 2D, they are. It's very easy to find the bounds, and it's easiest to go to polar coordinates. So little r goes from 0 to 6. And if I want to go all the way around the circle, one set of bounds for theta that will work is 0 to 2 pi. So I'll do that here. So since I'm switching to polar, I need 3 things. I need new bounds, which I found, and then I need my integrand in polar coordinates. So you have 14 times, remember x is r cosine of theta. So if I square that, I'll have r squared cosine squared theta. And then we have x times y. X is r cosine of theta and y is r sine of theta. So we're going to have r squared times sine of theta cosine of theta. And then we have a minus y squared. Y is r sine of theta. So that's r squared sine squared theta. So that's our integrand in terms of r and theta, our original integrand. And dA is r times dr d theta. Now we can integrate with respect to r first and then theta, or the other way around. Either one is fine because our bounds for r and theta are both constants. I see that all of these have an r squared in common, and then I've got this extra r out here. So I'm going to distribute that r in, so I'd have an r cubed for every factor, and then I'll factor out r cubed from everything. Or alternatively, you can think of factoring out that r squared from everything. R squared times that r will give us an r cubed. And then over here, we'll have sine of theta, cosine of theta. I'm going to use a trig identity to simplify that. And cosine squared theta minus sine squared theta. I will use a trig identity to simplify that as well. All right, now I'm integrating with respect to R first. Oops. There should be bounds for R. So with respect to R, all of this is constant, so I can factor that out. I can factor out the 14 as well. And the antiderivative of R cubed with respect to R, and from the power rule, add 1 to the exponent and divide by the new exponent. Evaluate at R equals 0 and R equals 6 and subtract. That 14 over 4 we can think of as 2 times 7 over 2 times 2. The 2's reduce. And then we'll have 6 to the 4th there, minus 0 to the 4th, which is just 0, times all of this. And of course, we could simplify further because 6 is 2 times 3, but we don't have to yet. I think I want to just evaluate this integral in terms of theta next. Now, there are a couple of trig identities that I want to use to make my computation a little easier. There's an identity that says that sine of 2 times an angle is 2 times the sine of that angle times the cosine of that angle. So this sine of theta cosine of theta is actually 1/2 of sine of 2 times theta. And there's another trig identity that says cosine of twice an angle is cosine squared of the angle minus sine squared of the angle. So this is actually cosine of 2 theta. So that is what I will anti-differentiate here, just using those identities. One of the 2's will reduce there. So 21 times 6 cubed. And then over here, we're going to have 1/2, bring that half down. The antiderivative of sine of an angle is negative cosine of that angle. If you've got a constant multiplying your angle, if we were to take the derivative, we'd have to multiply by that constant. To take the antiderivative, we've got to divide by it. And the antiderivative of cosine of 2 theta is sine of 2 theta. And if I was taking a derivative, I'd multiply by 2. To take an antiderivative, I divide by 2, evaluate from 0 to 2 pi. So we're going to have negative 1/4 cosine of 2 theta plus 1/2 sine of 2 theta. And I hope you guys can see that we're going to get 0 from this. Maybe it's not obvious. But let's see, when I substitute in 2 pi, I'm going to have negative 1/4 cosine of 4 pi plus 1/2 sine of 4 pi. Now cosine of 4 pi is the same as cosine of 0, which is 1. And sine of 4 pi is the same as sine of 0, which is 1. Or sorry, 0. Then we're going to subtract that 21 times 6 cubed times this, evaluated at 0. But again, cosine of 0 is the same as the sine of cosine of 4 pi. It's 1, and this is 0. So I've got this expression, and then I'm subtracting exactly the same thing. So I'm going to get 0 from this. I knew that was coming because I had these 2 trig functions, and I knew that they would have the same value at 4 pi as they do at 0. All right. So we were asked to do the following. We're asked to use Stokes' theorem to evaluate this line integral. Rather than evaluating the line integral, Stokes' theorem says you can evaluate the surface integral instead, and it turned out to be 0. Now, just to give you a sense of how you would set this up if you were to evaluate the line integral directly, that really isn't that difficult at all. C is this boundary right here. So I would need to parameterize C. And then once I have parametric equations for C. I would need to write my field in terms of t. I need to compute r prime because r prime dt is actually dr, and then I would have to take a dot product. So let's set that up. And then if it's not too difficult, we'll finish it. But if it is too difficult, you'll see the benefit of using Stokes' theorem in this circumstance. So I'm looking at this circle. It's a circle of radius 6. X goes from -6 to 6. Y goes from -6 to 6. It looks like the unit circle. It's just 6 times larger. Since that's the case, if I want to parameterize that circle, I can just take the parametric equations for the unit circle, cosine of t and sine of t. That would give us the whole unit circle as we go from 0 to 2 pi. And I can multiply those components by 6 to make it 6 times larger. So now x goes from -6 to 6, y goes from -6 to 6. And as t takes on the various values, we're going to trace out that circle of radius 6 centered at the origin. Okay, now in order to evaluate the line integral, we need a variable to tie everything together, and that variable we use to tie everything together is t. So we would typically evaluate the integral in terms of t from t equals a to t equals b of our field written in terms of, oops, we're in three-dimensional space. Let me write it this way. It's x of t, y of t, and z of t happens to be 0 as we are in a curve or on a curve in the xy plane where z is equal to 0. So I'll write our field in terms of t by replacing x with 6 cosine of t, replacing y with 6 sine of t, and replacing z of t with 0. And then dr is actually just r prime of t dt. So you can think of that as a velocity times a little infinitesimal time, which gives us a little infinitesimal displacement. We're taking that field and we're dotting it with the displacement, and we're adding those up. If that field represents a force, this would give us work. That field represents, let's say, the velocity of a fluid, then we would get circulation around the curve given by c. Okay, so I claim that if we evaluate this integral, we're going to get 0, the same as we obtained using Stokes' theorem. Remember, our field looked like this. In order to use this, to evaluate this, I need this in terms of t. So I need to replace x with 6 cosine of t, z with 0, and y with 6 sine of t. So I'm just opening up some parentheses so I can substitute x equals 6 cosine of t, y equals 6 sine of t, z equals 0. So we're going to get 0 times I hat plus 6 sine of t times j hat plus this 7 times 36, whatever that is, times sine of t times cosine of t. And we could simplify further if we wanted to. We'll see if we want to in a bit. Now I want to take the dot product of that with r prime. So I need to compute the derivative of r, which is easy enough to do. I'm just going to take the derivative component by component. So of x prime, y prime, and z prime here. And of course, z prime is 0. Derivative of cosine is negative sine. Derivative of sine is cosine. So we've got that. And then we're going to take the dot product of f with r prime. This is very easy. So you take 0 and multiply it by this, and then you add this times this, and then you add this times this. So we've got 0 times something, which is of course 0, plus 36 times sine of t times cosine of t, plus another function here, But again, it's multiplied by 0, so we're just going to get 0. So you don't have to write that down. Just writing it down for emphasis. That's our integrand. And again, I can use that trig identity. That is 18 times 2 sine of t cosine of t. And 2 sine of t cosine of t is actually sine of 2t. So I can integrate this function rather than integrating that function. If we integrate this with a u substitution, we're going to get the same result. It's just easier to anti-differentiate this function. Okay, so the line integral over c of f dotted with dr is the line integral, or excuse me, the regular integral from t equals 0 to t equals 2 pi of f dotted with r prime, where f and r prime are written in terms of t. And that's a very easy antiderivative. Bring the 18 down, the antiderivative of sine is cosine. If I've got a constant inside, I have to divide by that constant, evaluate from t equals 0 to t equals 2 pi. So we get -9 times cosine of 4 pi, factoring out that -9 minus cosine of 0. So you get 1 minus 1, which is -9 times 0. So we get 0. That was actually not that bad. And we really didn't need Stokes' theorem in order to evaluate that line integral. But we see that if we use Stokes' theorem, the surface integral over the surface, which is given by this, is the same as that. And we were asked to use Stokes' theorem this time. So we want to evaluate the surface integral and show that, or find the value of this line integral in this way. But it's nice to confirm that the left-hand side and the right-hand side, the line integral and the surface integral do give us the same thing. And that's what we've done here. I hope that helps. Let me know if you have any questions.